Good morning, everyone. Today we continue with our PoligonSoft free class. In the previous class, we had created two finite element mesh models. We had done this example that we see on the screen. It's a permanent mold casting model containing its mold, and inside we can see the part we are going to cast. It's a classic simulation where at the end of the simulation, we will obtain all the complete results, meaning the mold temperatures and the part temperatures. Additionally, we had made a second example, a second mesh, which is the mesh we can see. It's a mesh for a sand casting, but since it's a part with large dimensions, and the PoligonSoft free program has a limit of 500,000 polygons per simulation, we had agreed that we would do this simulation without the mold. We are going to use a PoligonSoft function called virtual mold to save us the mold calculation and obtain the results just for the part itself, without having to create mold meshes and without using polygons for the mold. We can still do this type of simulation and obtain a quite accurate result without creating molds. Let's begin. The first thing we need to do is go to the program's initial window and run the master module. This is the module where our simulation will be assembled. Here we can see the program's initial window. First, I'd like to talk about the language. PoligonSoft is a multilingual program, meaning we have English, Spanish, Chinese, and Russian languages available. To change the language, use the F3 key on the keyboard. We can press it and see that the program changed to Spanish. Similarly, we can change it to Russian and also change it to Chinese. Today, I will be working in the English version of the program. Why in English? Because if we press F1, which is the command that allows us to open the user guide, we can see that the user guide is in English. And since our class is a beginner's class, it doesn't cover all the working modes in the program. There are many things I won't have time to talk about because the simulation can have many more parameters than what we will do in today's class. I always recommend, in case you have any doubts, in case you don't understand how to simulate a certain process, you can always refer to the user manual. It's a very complete manual with examples. It's a very convenient manual and can be used to learn how to use the program. Let's begin. I'm going to close the user manual and let's start working on our simulation. The first thing we obviously need to do is open our geometry. We click the Open button. Here we select the last parameter, Salom, which is the format of our meshes created last time. We leave the units in millimeters, click OK. Let's start with the first example, Lesson 1. Our geometry has loaded. As we can see, a warning window appeared asking if I want to load the parameters from the previous simulation or not. What is this and what is it for? The thing is, we are doing our first simulation and it doesn't matter if I click yes or no now. But if we were doing real work, the program allows leaving all the settings made in the previous simulation and loading only the geometry to be able, directly, without any other changes, to run the simulation. Since today we are doing a job that doesn't have any preset parameters yet, we will select No to load the default parameters. We now have our model. We can see our model, and here we will talk about the settings we need to make before starting our simulation. First, I'll talk a bit about navigation, about how to work with the graphics. It's very simple, very similar to CAD programs. To rotate the model, I press the left mouse button and move the mouse. I can rotate it as I want. To zoom in or out, you use the mouse wheel. And to move it within the window, we press the right mouse button, and I can move it as I desire. On the left, I can see the structure of my model. To start talking about the parameters we need to set, I will switch to the Modes tab, and we'll talk a bit about what we have here and how to use it. The program has 3 working modes. The first mode is the volume type. The volume type is this branch we can see here. We have 3 volume types. one for our elements that will be cast, the other for elements that will be parts of the mold, and one which currently has no elements in it, used for additional volumes, or in case I don't want some part to interact in the calculation I'm doing, I can move the elements to the void part, and these volumes will not be used in any way in our calculation. Volumes corresponding to the casting are always marked in red. Elements belonging to the form or mold volume class are always marked in blue. If I want to change, for example, when I open my model, I have everything reversed here, because this is set semi-automatically and at no point does it ask us what element is what. I can always move them. For example, if I move the casting down, I can see that all my elements have now become a mold volume. I'll move it back. So the first step we always take before starting is in this branch here to select the elements that refer to the casting, select the elements that refer to the mold, and place them in the corresponding branch. The second parameter we need to set is the volume index. What is a volume index? Simply put, the volume index is the material being used in a specific volume. I'll switch to the second tab of the left window, and here we can see our indices that we will use. I have a separate material, which is the material of our molten metal. Here, obviously, for all volumes within the casting partition of the casting volume type, the material will always be the same because I don't think we are casting different types of metals in a single casting. The first thing we'll do here is set the material for our casting. We click the pencil icon, and the material database opens. I can create a new material here, apply all the parameters I need to run a simulation. These parameters, there are many ways to obtain them. There are catalogs with material data. There are laboratories that can perform tests on the material you are using. There are even programs that allow, based on chemical composition, calculating and predicting the parameters of our material. But for the work we're doing today, we won't talk about this part. It's very well explained in the user manual. We will simply click the Import button and open some aluminum. I don't know, let's say this one. There are quite a few materials in the database. You can always find an analog of your own material or get these parameters from the material manufacturer, who almost always has them. Our material has now loaded, and this material will be used for our casting. We click Apply and close the window. All parameters here, if desired, can be edited, can be adjusted according to your needs. Everything here can be changed. Now, as I can see, for my material, I have set an aluminum ADC12Z. What's the next thing I can do? Let's talk a bit more about volume indices. In the Materials tab, I can see that I have 9 different indices available. Index 2 is marked with a plus symbol. This means that Index 2 is now assigned to our mold volume. If I double-click on our mold, a tab will open where I can put any index I want. Index 3, OK. We see it change color and now corresponds to the green index color I see here, and the number 3. Let's go back. Here we can see the volume type, casting mold. Here the volume index, meaning the material assigned to our mold. The part material is only one for all volumes here. For the mold, I can use up to 9 different materials for different indices. This still has index 3, which doesn't correspond to any material. To change it, just like with the casting material, we click the pencil, Import. Let's say this permanent mold is made of some steel. Let me select a corresponding steel. There. I assigned a material to our permanent mold. As we can see here, instead of a line with no information, we now have the assigned material. In case I want to assign another material, I don't know, anyone, just so you can see what I'm talking about. Here I can see that in my database, in my structure, I have the material GS45, which is currently assigned to our permanent mold. But also by double-clicking on our mold, I can change it to another material and everything will change immediately. I'll go back. Besides the materials, at this point we have already established the material for the casting, the material for our mold, which in this case is a steel. What's left to do? We need to set the last type of data, which is the boundary index. This is a bit more complicated, let me explain. When we assign a material to the mold, this material has its thermal properties, and these properties will be used to perform calculations for everything inside the mold. However, heat transfer between different materials is a parameter that has nothing to do with the material's thermal properties. In the case of the casting we see on screen, we have several heat transfer indices. They are called boundary indices in the program. What indices are they? If I switch to the main tab of our program, I can see there's a key, a button called heat transfer. In our case, there are no indices assigned yet. Let's import parameters. Click the import button and open some preset parameters. Here I don't really have permanent mold casting, but well, I'll select pressure die casting, which is the closest, so you can see what I'm talking about. A list of boundary indices opened, showing us the following. First, I can see that our mold's exterior has a light blue, almost violet color. That color corresponds to index 18, which is the heat exchange between the mold and the environment, meaning how our mold will be emitting energy to the surrounding environment. On the outside, similarly, I can see that our part has an orange color, which is the heat exchange between our casting and the environment. Also, if I now turn off the mold's visibility, I can see that between the part and the mold, there's another index that was automatically set as index 1, which is the heat exchange between our casting and our mold. In case I need to change a parameter here, for example, the transfer between my casting and any name I desire, I can simply set the parameters here. Let's say the heat exchange will be 2000. These parameters are much debated. There are numerous scientific works related to what heat exchange value to put in different situations. Really, if you don't have much experience, you can use the default parameters that come in templates with the program, but you can also put any parameter you need here, even curves. I can set that from 0 temperature, the exchange will be 500. For a temperature of 600 degrees, the exchange will increase to 1000. And for a temperature of 1000 degrees, the exchange will rise to 2000. For example, I have created a curve showing the dependence of heat exchange between our casting and our mold. Normally, why does this happen? Because while our part is in a liquid state, the contact with the mold surface is much greater than when it starts to solidify. As the part solidifies, it begins to contract, and the contact is no longer perfectly ideal. Gaps start to appear. This causes the heat exchange between the mold and the part to decrease. That's why normally curves of heat exchange are used instead of constant values. You can obtain these data yourselves. You can do test castings using thermocouples to determine the actual heat exchange for your castings, or leave the preset parameters that come with the program. In case, for example, I now have the boundary index set for the heat exchange between our casting and our mold with index 1. If I want to switch to the parameter I just created, which corresponds to index 2, I close this here, go to the Edit tab, and execute the Select Boundaries function. I want for my casting to change from the first to the second. I select here, indicating I'm selecting elements with index 1. I've selected them. Click Assign Index and we put index 2. As you can see, our boundary index changed completely. Now index 2 is assigned. If I turn off our mold, I can see that the same index was assigned to the mold on the internal side, since obviously the heat exchange index will be the same for the parts in contact. We have now finished with the parameters that need to be set. The last thing remaining is to check the coordinate system. To see the orientation of my part and in which direction the calculation will be performed, I recommend clicking the Reset Rotations button. I'll turn off the visibility of our mold. Here, everything is fine. The direction of the gravitational force in PoligonSoft is always directed along the y-coordinate. As we can see here, y is upwards and our mold is in the correct position. In case we encounter any problems with the coordinate system when opening our model, I will show you exactly how to do it in the second example. In this case, everything is fine. We don't need to make any corrections. And before starting the simulation, the last thing we need to do is, in this same Edit tab we have here, execute the Mesh Check command. This one here, check our mesh. Why do we need to do this? If you remember from the previous class, we executed a mesh correction command, but we only corrected the two-dimensional mesh. We created the 3D mesh completely automatically and performed no quality checks on it. Here in the PoligonSoft program, we have this button to check the quality of our mesh. But as we can see, everything here is 0. Our mesh completely meets all necessary requirements and can be used without any problem to perform the calculation. If there were any problems here, we could have clicked the Correct button, and if correcting elements wasn't possible, simply delete the elements that are bad. If we delete several elements, they won't participate in our calculation. That's not a problem because we're normally talking about 3 or 4 polygons in a 500,000 polygon mesh. They won't interfere with the calculation in any way. Okay, we close this here. Simulation, and now we'll run it. Click the Start Simulation button. Here, before starting the calculation, we need to set several parameters. In the General tab, we need to set the temperature of our casting, the temperature at which the simulation will run for our mold. If it's a mold at room temperature, we simply leave the same temperature as the environment. If it's a preheated mold, we can put here, since we're talking about a permanent mold, let's say the mold temperature will be 300. The ambient temperature, let's say 27 degrees. The casting temperature, the technologist usually knows this. Since I selected a material I don't know very well, I'll check the material's solidification temperatures. If I look here at the solid fraction curve, I see the material completely solidifies at 540 degrees and is fully liquid at 575 degrees. So let's say the casting temperature for our material will be, let it be 700 degrees. All right, done. The second tab is dedicated to the filling calculation. But since this class covers working with the free version, we cannot select Calculate Filling here, simply because when running the calculation, the program will state that no license is available, and you cannot use this mode. Therefore, the Flow, Stress, Heat Treatment, Structure tabs must be turned off. We cannot select these modules because the simulation will not run. Let's go to the Solidification tab and see what we have here. It must be enabled. Here we tell it which results I want to save. I obviously want to save the results for my casting and will save the results for my mold. Regarding the calculation step, you set this parameter according to the work we are doing. This casting is a permanent mold casting that will solidify quite quickly. I think this will take 17-20 seconds, no more. So here, we put a very small step, I don't know, 1/10 of a second. The other parameter we need to set is the step at which our calculations will be saved. This doesn't influence the calculation in any way. It simply influences the number of steps we can analyze in the results analysis process. You can put the same parameter as the simulation step, but this will cause our simulation file to be very, very large. Therefore, I recommend always putting double or triple the simulation step here. And for different jobs where we are not interested in the dynamics as such and only need the final result, you can put an extremely large step here, just ensuring it fits within the calculation time. Here we also establish that our simulation will end when the temperature of our casting reaches the solidus temperature. Here we can also set a fixed time or a calculation stop temperature. Normally we leave this at T solidus. And one very important thing for the calculation to run in the free version, we have to uncheck the option to use initial temperatures after filling. Why? Because since we are not calculating the filling, this data will not be available, and running the simulation will result in an error. We have several porosity options here. The program PoligonSoft has 2 porosity calculation models. Well, first we need to select that yes, we are going to calculate porosities, and we'll use the classic porosity model because it's the simplest and requires no additional adjustments. If you want to use the new porosity model, you can select this option here, but I recommend first reading the documentation, the user manual, carefully before doing so, because you need to know how to do it. In our case, we will leave the parameter use microporosity enabled to calculate porosities in the classic way. The other parameters, if I need to know pressures, there are several parameters here, but they are not normally used for simple castings. Our simulation is now ready. The only thing I forgot to mention is that in the General tab, here we can set the number of processor cores we want to use. In my case, I have a fairly simple computer with only 4 cores. In case you need not to use all the computing power available on the computer, or conversely, use all available power, enter the number of cores the computer has here, or simply enter the maximum available cores. The program won't be able to use more cores than are available anyway. If I put 8 here, only the 4 my computer has will be used. But here you can enter a number that should correspond to the number of cores you have in your processor. Ready? We can now run our calculation. Let's begin. Click Start Simulation. We save our file now in the PoligonSoft program format, so we can open it if we need to make any changes in the future. And we can see our simulation starting. Since I had set 4 cores, the program is using 4 cores for the calculation. An error message appears here saying that a commercial license was not found. This error is normal. We are using the free version, so the program doesn't have a license, as I mentioned before. The interface of the paid program and the free program is the same. The only difference is that with the commercial version of the program, we can use all the available parameters, the filling parameter, the calculation of, the calculation of stresses, deformations. We can calculate heat treatments. For the free version, only solidification and porosity are available. Once we've run the entire simulation, I don't really need the program itself anymore. I can close it. I'll save what I did. The calculation will continue without the program. This will take a little while, but not too long. Really, the calculation of 500,000 polygons that we are doing takes about 3 or 4 minutes to calculate. But to avoid waiting, I'll speed up the video a bit. All right, done. As we can see, our calculation has finished. We just need to press any key on our keyboard to close the simulation. And now let's see what we have calculated in order to analyze the results. Let's run the Mirage module, which is the third button in the PoligonSoft program's main window. This is the results analysis module. We had calculated two parameters, solidification dynamics and porosities. Let's start with the solidification analysis. For this, we click the Open Temperatures button, the first one here in the upper left corner. In the same folder where we ran our calculation, we will find a file with the same name as the project we saved in the master module, and with a part that says solid. This means that this file is the solidification file for our simulation. Open. Okay, our casting opened here. I'll bring it to a view more similar to what we need. I'll remove all cuts. I'll talk more about cuts later. And let's see what we have here. We are now viewing the first second of our casting's execution. I'll also turn this off here so the results are displayed. On the scale, I can see I have a scale from 100% to 0% solidification and two additional parameters which are 500 and 200 degrees. I can change any of these temperatures at any time. I can simply type the temperature on the keyboard and set it so it can be seen. If I need to create a distributed scale, I deselect the parameters and tell it I want to get from 100% to 0%. And the program recalculates all the steps so the scale is distributed. Click Apply for the scale to change, and let's see how to analyze it here. By clicking the Play button, I can go step by step watching how the solidification of my part progresses. But since it's quite difficult to understand what's happening inside the part just by looking at the surface temperatures, for solidification analysis, the solidification isotherm is normally used. If I select this option here called ISO Surface Parameters, I can tell the program that I only want to see the parts that are, for example, at a solidification level above 0%. Meaning the entire part that is already completely solid will not be shown. We will only see the part that has some percentage of metal in a liquid state. And I can already see that, for example, in these vents up here, part of the metal has disappeared because all the solidified metal is no longer shown. I can advance through our results. If I'm interested in the temperature at a specific point, I can double-click and establish temperature points. To remove these markers, I either double-click with the right mouse button on the marker or press Ctrl-D for all of them to disappear. It's a bit non-obvious, that's why I mention it. Double-click with the left to place it, double-click with the right to remove it. We continue watching how our solidification progresses. Everything is still fed, but at this moment we can see that a problem has occurred. Our feeding system became completely isolated from our part, meaning a hotspot appeared in the lower section, which obviously upon shrinking will cause problems on that entire surface area. Now we'll look at the porosity to analyze where the problems occurred. Let's keep watching. If I want to take a larger step, I can advance more quickly, or I can set the time I'm interested in simply using this slider. Now, the visibility of my entire model is controlled just like in the master module by selecting the options available down here. For example, if what interests me is the mold temperature and not the part temperature, I can make a cut. I select Show Mold, turn off the visibility of our casting, and activate the Mold Cut view. To control where our cut is located, here we have a button called Switch to Set Cut Plane Mode. What can I do here? If I activate it, I will see my section plane as such, a surface that allows me to see where the cut is currently located. If I want to change the section plane, I can use these buttons here that allow me to rotate it relative to my model. If I want to move it somewhere, for example, I want to set it here in the middle, I double-click where I need to set my cut. And to confirm, I can click the button next to the mode change right here to confirm my selection. The program asks if I want to do it for the mold in the part. I say yes. And obviously, as we can see, we now have the data for the cut here. I'm going to turn off the cut for the mold. I simply want to see the temperatures for the mold. Everything here is a single color, simply because our mold is completely colder than the lowest point we have on the scale. If I check, for example, here I have a temperature around 300 degrees. Here I have a temperature of 300. Yes, because it was preheated. Let's do something so it's visible. Here we set the maximum temperature to be 500 degrees. The minimum temperature to be 300 degrees. We've now set the temperatures for our mold, and we can see in the cut how our mold is heating up. In case you find it more comfortable to work with boundaries that are not gradient-based, you can turn off this button here. Then the blocks will have defined limits, without fading, meaning we know exactly that this here is temperatures of 300, this here is temperatures between 300 and 325. This here corresponds to the difference between the two levels. Okay, I'll go back. Let me remove this. With this button, we can return to the default parameters. This allows us to reset the default parameters for the colors, this one for the values. Click Apply, and I return to our default values. Turn off the mold cut. Turn off the mold. Return to our part. Nothing is visible here simply because we are at the last step where everything has already solidified. If I go back one step, no, nothing is visible here simply because I have the isotherm set for 200 degrees. And I have the mold turned off. In summary, what can we see here? The solidification analysis determined that if we look at this part, at the 18th second of solidification, the feeding channel becomes completely isolated from the part itself. And this will obviously cause porosities in this area here, as it's an unfed hotspot, and since we don't have molten metal to compensate for the shrinkage, porosity will form in this area here. Let's look at the porosities we obtained in our calculation and see what we can do with them. To avoid closing this window, I'll open another copy of the Mirage module. Click the Open Porosity button and open the corresponding file, which is the file where the porosity was calculated. Done. In the first step, obviously, we don't have any porosity, but regarding porosity, we're not so much interested in how it forms. Therefore, very quickly, I'll jump to the last step and we'll see what results we obtained. To begin, just as we did before with the solidification isotherm, here we can set a level of porosity that will be displayed to see defects inside the part. But first, I'll completely turn off the isotherm to see the surface porosities. As we can see, according to our scale, which shows porosities from 0.7% up to 90%, which is already a complete shrinkage cavity, a hole, we have several defects on our surface, but if we look closely, these defects are very, very small porosities, 1%, 2%. And on the other side, we have porosities. The maximum porosity is this little dot we have here, which is a porosity of 0.5%. Actually, for a part of this quality and from this casting, I imagine the quality of the obtained part will be sufficient, and we really won't have to change anything in this model. However, if we had needed a part with a higher quality level, I think the simplest thing would have been to slightly enlarge this channel. This channel is where we lose feeding, and if we increase its dimensions towards the mold, there will be more metal here, and then the loss of feeding will occur later, and we can obtain fewer shrinkage defects. Let's see what else we can see here. Just like we did with solidification, to see porosities inside the part, we can activate the isotherm mode. And say that, for example, I want to see all the porosities I have that are greater than 5%. This limit is set by your company's technologist, depending on the required quality for the job we are doing. Because, for example, for parts that must have high strength, sometimes zero porosity is sought, meaning there can be no defects. But for common items, porosities of a 5% level are quite acceptable, and we can leave the model as it is. As we can see, the only area that has problems is this area here, which contains shrinkage defects inside the part. I'll raise it up to 10% to see in more detail where the problem is. Exactly, the problem is in this area here. If I want to see how the porosity is distributed inside my part, I'll turn off the isotherm again and make a cut. Just like we did last time, switch to the Set Cut Plane mode. First, I'll see what happens in my feeding channel. This is a class, so we can do this. Click Apply. And as we can see inside in the channel, we have porosities up to 2.5%, and obviously the shrinkage cavity that occurred during the solidification process of the metal above it. There are some 100% porosities here. To see the part I'm interested in, I switch back to the Set mode, double-click on the area I'm interested in, and confirm the change. We can see that inside the part we have porosities, but these porosities are not very high. We're talking about a maximum porosity of 11%. And as I mentioned, if this had been a real job, it seems to me it could be left as is. No change is required here. We have confirmed that our design is acceptable, that our design can be used for a real casting and doesn't need many changes. Actually, in a real job, we would have needed to make several more changes. For example, I almost always recommend running the calculation for various temperatures, starting from the minimum temperature and ending at maximum temperatures, and in this way find the optimal temperature for our casting, the temperature that will allow us, with the lowest costs, to achieve a part with the fewest possible defects. I'm talking about this, meaning there could be another calculation with 650, another calculation with 720, with 740. The PoligonSoft free program allows you to perform as many calculations as you wish, as long as it involves a model containing fewer than 500,000 polygons. Actually, today I wanted in the class to show you how to do the simulation with the virtual mold. But since we spent so much time on the first part, I think we'll do the following. For today, we will finish. We have learned how to do simulations, learned how to analyze the data, and in the next class, we will be doing this model here, which will be a simulation using a virtual mold. We have finished for today. Thank you very much for your attention. I hope the information has been very useful to you and that you will be able to use the program to carry out your real work. Again, I repeat, the PoligonSoft free program does not require any type of license and can be used for your work without any limitations. Thank you very much. See you soon.